And we are live. So Linux Girl, do you want to go ahead and do the intro?
Yeah, so let me do the intro. So I wanted to first thank you everybody who attended this. I know some people are not local here. I know ARV is probably from Denver. So just because I kind of talked to him this morning, but I wanted to welcome everybody. And you know, White Rapid, Jason, I've known him for 4 years now. I know it has been crazy, and I still remember, you know, the time that he actually invited me to his, he was a president of El Camino Cybersecurity Club. He invited me to a talk that was done by Lieutenant Colonel, and she was a female cybersecurity person, and it was great. So throughout the years, you know, I know what's going on with the White Rapids life. You know, we're looking at resumes, you know, internship application for computer science major to Berkeley and whatnot, and then grad school. We talked about so much, and I want to, White Rabbit, thank you for doing it. I want to, first of all, I want to let everybody know White Rabbit just got his internship with Cisco. Yeah, let's do a virtual cloud. That was exciting to hear that, because I know I've been keeping in touch with Rabbit for, you know, for throughout the 4 years. So in terms of the school and White Rabbit, yeah, so thank you. So I wanted to just congratulate you, White Rabbit. It's really great to know I know you're a smart person. Like I said, you're going to be doing really, really well. And then I think also White Rabbit, you're going to be graduating fall semester. So can you give us free hardware? So I wanted to just read out something from his meetup, the page he provided to me. His alias, Jason is White Rabbit, and he's currently undergraduate student at UC Berkeley, and he plans on graduating this year, like I mentioned, in the fall semester. He will start his early career with Cisco Systems, and he's super excited about this. And when he was at the El Camino Community College, he got really involved with many cybersecurity groups, including this one. And the SBWASP was actually his first one. And he was a president of the cybersecurity club at El Camino. Like I mentioned, I actually attended to one of his talks. So I really have to say, I'm really, really excited about this presentation. I don't know too much about hardware, and I've reviewed his presentation slides already. This is going to be a good talk. I know he prepared a lot, and the title of his presentation is Computer Architecture Basics and the Spectral Explained. So without any further ado, please join me to welcome Jason. All right, Jason, I'm turning over to you.
All right. Hello, everyone. You guys hear me okay?
Yep, loud and clear.
All right, cool. Yep, I'm a UC Berkeley undergrad, gonna graduate this year, so ready to join the workforce. It's a huge change, but all right. So yeah, I just wanted to share with you guys, with my OG group, some things that I've learned relating to cybersecurity and something I'm very passionate about, which is computer architecture and hardware design. And one of the labs that I did was on Spectre and Meltdown. So I just wanted to share with you the things that I learned. Okay, go to the next slide. Oh, and again, if you don't understand something, just please interrupt and ask questions. So I just wanted to acknowledge some of these slides are property of UC Berkeley, and I'm only using these for educational purposes. I'm not copying an entire lecture from UC Berkeley. So just wanted to talk about the motivation, like why should we care? I mean, computers, you know, they're a fairly new thing in society, right? Computers didn't really enter the world until didn't become really relevant till World War II, right? Cracking Enigma, calculating artillery trajectories, and then, you know, later becoming more and more advanced, a lot smaller, the invention of the silicon transistor, which eventually led to the microprocessor, blah, blah, blah. So like, basically what I'm saying is that there's been a long development process since, the birth, you could say, of computing all the way up to what it is now. And there's been a lot of design choices to make computers as fast as they are now. And some of those choices, even though they've, made our lives better, made computers faster, are actually flawed, and are actually now, looking back now, a lot of senior hardware designers, like I can't remember their names, but something Patterson, something Hennessy, the founders of the RISC architecture, which RISC right now is like used by 90% of the world right now. It's like basically any microprocessor that's embedded or on your phone or on a tablet, and even modern processors, or not modern processors, desktop processors and supercomputer processors use the RISC architecture. So like, and now those guys, the founders, are now saying, look, we never thought about security, and like now we got to start considering it, because Spectre and Meltdown have proven that the things that we relied on for optimization are now like the biggest flaw. So that's kind of the motivation behind this. Like why should we care? So like I said in the meeting, or in the description of the meeting, just wanted to talk about a little bit about what is computer architecture. So the thing to understand is that when you use your computer, right, when you're on the operating system and you're using programs, or you're compiling code, or you're writing like a simple Python script, right, your hello world, there's a lot going on. And usually like the term is called turtles on turtles. Basically there's just layer on top of layer on top of layer, all the way up to the high level, right? So like here, this is what we know, this is what we use, right? C, Python, and then these go up in terms of abstraction, right? Like Java, for example, right? C is probably the closest thing to like low level that usually most people know, right? And then you have assembly, which gets even lower, which is what the compiler turns your high level programming language into, which then turns into machine language, or just like strings of 32-bit strings or 64-bit strings of binary numbers, right? Which then goes into, your hardware architecture, and then that eventually becomes, voltages on transistors in a circuit. So there's a lot going on. So I'm gonna focus on like this level here, or actually, I'm sorry, this level here is more on the lower level, the architecture side. Let's see, you got a question. Have you read about the project University of Michigan took on? No, I haven't heard of that. I'm kind of out of the loop on a lot of things just because, school and stuff. So I'm not just focusing on classes. So I'm not really like up to date on a lot of things. So yeah. And then here's like, I guess you could say a cute little video, turtles balancing. So yeah, so everything just kind of like builds on top of that, right? Builds you from the transistor all the way up to, for sure, the transistor all the way up to the digital circuit, which then the digital circuit runs off the binary, and then the binary runs off the C code. Or I'm sorry, not the C code. The binary, which then becomes the assembly, which then is the C code. So that's kind of the layers that are going on. So keep that in mind. So, all right. So I guess the first thing I want to talk about is what is a digital circuit? So we have these things called transistors, right? Which we all know and love. And I guess the transistor that we're all familiar with is the not familiar. I'm sorry. The transistor that is most commonly used is the CMOS transistor. And the C just stands for complementary, and then MOS, which is metal oxide semiconductor. So these are the transistors that are used in basically all modern circuits today. Like this was the breakthrough in computing. It was making these silicon transistors. I won't go into the details. I mean, unless you're curious, I could a little bit about how these things work. Involves a lot of like low-level physics, things operating on the I think it's the quantum level. I think that's the right way to say it. Where you have NMOS, right, and then you have PMOS transistors, and the difference between them, a simplified or a more abstracted way to think about it is that NMOS is like your high is on and low is off. And then PMOS is the other way, which is low is on and high is off. So they're complementary to each other. So, and then the difference is that NMOS have, let me know if this gets a little too too out there, but yeah, so the NMOS uses a P substrate, and P just means it's a donor. So I guess maybe I shouldn't talk about this, but I mean, like usually solid material, the atoms form crystalline structures. So silicon has this structure where it's kind of like a cube. So you have this cube-like structure here, and they have these connections, right? And these connections are free electrons. And pure silicon is perfectly connected. And current, which is how electricity works, right? It's the flow of electricity, the flow of electrons, will not flow through this. So that's why it's called a semiconductor, because it doesn't. You could dope. It's called doping. You could dope it with either donors or acceptors. So acceptors are basically these crystalline structures where they're missing an electron. And or not donors, I'm sorry. Acceptors are the ones that are missing. And so basically if an electron's flowing, it'll just get stuck here and fill in the gap. Where as a donor is, the donor material is just allowing electrons to flow. So basically here you have extra electrons, and then something that will accept electrons. And when you apply a voltage here, due to some physics, and which I will not talk about, you create a channel which then connects these two things. And that's how you have a switch. So basically when this voltage difference here hits a threshold, it's on. It's like a switch that closes, and you can allow current to flow through it. And it's the other way for PMOS. So PMOS is, you have P's here, acceptors here, and then the donor here. The substrate is now the donor. And like I said, don't worry too much about the details. All it is just you apply a voltage difference, the switch turns on. And PMOS is a low voltage turns it on, and NMOS is the high voltage turns it on, a high voltage difference. And there's ways you can manipulate these things, but essentially that's how MOSFET transistors work. So that's like super low level, right? Like these are like analog circuits. So from these analog circuits, we can make, let me go to the next slide. Oops.
So Jason, so for CMOS, what pops into my head is like a BIOS. Is that more of a coincidence, or has nothing to do with necessarily like the BIOS of let's say a motherboard or anything? Or that's just the technology that's on them.
Yeah, BIOS. I'm not super familiar with BIOS, but no, but CMOS is just it's more of like a material electronics term. It just means that the
Gotcha. Because
it's
I also think like for MOSFET, I do know like in audiophile land or like in car audio or amplification, MOSFET is traditionally talked about. So I think that maybe is a better correlation because I think that in that instance there is a relation to actual transistors and amplifying signal. So does that
yes,
make sense?
yeah. So transistors, besides being used as digital circuits, are also used as can also be used as amplifiers to signals. So if you have like a small signal that's coming in, it goes into a circuit. I'll just draw this circuit here. It'll go into the circuit, and this is supposed to be like an amplifier, but this is like a really bad. But I'm intentionally leaving out details, because otherwise it's gonna get too hairy. Um, and it'll basically amplify. So transistors can be used to amplify circuits, so that like you could have a threshold, and when it crosses that threshold, that small because NMOS or MOSFET transistors and any transistor in general rely on what's called small signal. They have small signal characteristics. So usually, large signal characteristics is is used when is when the transistor is used as a switch. Whereas in small signal uh, I think it'll help if I draw this little graph here. So like basically here you have like the voltage, and then let's say here you have the current. And the current I'm talking about is the current flow between the transistor that goes through the transistor. And then the voltage is the voltage difference on the transistor. And so as you increase the voltage, it's not discrete. It doesn't just like go up and then you have your constant voltage. It's gradual. So like you have these phases where it kind of goes up, and it becomes linear. It becomes like a linear function basically. So the relationship between voltage and current is linear, like a line, like a slope. Um, and then as you increase the voltage, it eventually reaches saturation, which is what is used in switches where you have this constant voltage, and it won't go any higher, and it will go lower if you lower the voltage. But as long as the voltage is high enough, it'll reach saturation. No matter how much voltage you push through this transistor, it'll remain constant. So this whole area right here is known as the linear triode region. And usually, like, these are small voltages. These are really tiny. And so you can exploit this fact. And that's what amplifiers, transistor-based amplifiers do, is they exploit the fact that these small signals will make the transistor behave this way, which then could be used to amplify circuits. So that makes sense why it would be used for cars, because there's two types of transistors. I mean, you have CMOS and then you have BJTs, which are kind of like the older types of transistors. They're not as good, but they serve very specific purposes. Anyways, that's like pretty deep on transistors. But so those are transistors. And I can see why they talk about, well, what kind of amplifier are you using? Are you using a BJT based, or I don't know. I don't really know too much about car audio systems, but I do know that transistors, those two types of transistors can be used for amplifiers. So yeah, so that's transistors. So transistors could be used as, oops, why isn't this erasing? Okay. Logic gates. By basically having this, I guess you could say, topology of transistors, you can create different kinds of logic gates. So here, if you apply a high voltage here, then what's going to happen is that this is going to turn off, right? Because this is when you see a transistor that has like a little bubble here, that means that it's a PMOS transistor. And so high voltage will actually close the gate, or not close the gate, leave the gate open. So this, the high voltage here, will never flow here to V out. Whereas here, the high voltage here will close the gate, so this will be open, right? And this will be closed, and this just basically means ground or 0 voltage. So you can think of this as like a high voltage, like 5 volts, and then this is a low voltage, 0 volts. So if you apply like, let's say 5 volts here, this will open, so there'll be no voltage difference here, and then this will close, and so your voltage here is now 0. So basically, and then if you apply a low voltage here, let's say 0 volts or even negative voltage, this will close and this will remain open. So now your output voltage is 5 volts. And so you can take this and abstract it and just say this is a NOT gate. And then from these like structures that we can make using transistors, we can make even more complex logic gates. Like here in this instance, this arrangement of transistors are in a NAND gate, basically. And there's like ways, there's, if you ever take like a digital design course, you'll learn how to create all kinds of Boolean algebra functions. But in this case, this is a NAND gate.
And for these what we're looking at, these diagrams, what scale are we looking at as far as size? I mean, I know this is like abstract, like a drawing of the topology, but how are we talking, like microns, or are we talking inches, or?
Well, definitely. What is it? Definitely on like the. Well, this is overly simplified. This is definitely super abstracted. But I mean, like, I guess you could see like the layer. I mean, there's a lot that goes into making like a digital circuit, right? Like a digital circuit, because you have like the different layers, and then like the silicon layers, and then they have to dope it, and then they have to cut it with those super expensive lasers. But I would say, as like a guess, that like a NAND gate would be, I would say, like on the nanometer level. It would be extremely small. And I guess I could come back to that. I have a picture of like a die, and it would be really small. It would be extremely small. I mean, typically, like every company has a different way of advertising how big their transistors are. Like 7 nanometer, AMD says 7 nanometer, Intel says we have 14 nanometer, but it's really 7 nanometer. So like there's different ways that they measure the size of the transistor. So I guess it would be hard for me to say like exactly like the size, but it'd be extremely small. This is like on the net, like, yeah, micron level. Like you would need a micron scope to be able to see these things. So yeah, does that kind of answer?
Yeah. Yep. Perfect. Thank you. So, yep. Thank you.
Okay.
I think, JC, you can actually show a picture or whatever that you said you were going to show to just demonstrate the size of it. I think that would give us a better idea.
Sure.
And yeah, I mean, you don't have to do it now. I'm just suggesting, because this is like really, for me, it's like I only took one electrical engineering course. I barely remember anything, but this is just kind of hard. I am not a hardware person, but I'm glad you're going over that. So thanks.
Yeah. Yeah. I mean, like, I wouldn't, just the thing to take away from this is, we have transistors, and then transistors make up logic gates, which in turn make up digital circuit. And I'll go more into that.
Yeah, I think that's just a great way of saying that's what's, what you just said. I mean, that one I understood that, but thanks.
Yeah, for sure. I guess I could just show you guys real quick and come back to it. So like here we have a die or a chip. This is a processor. I don't remember what processor this is, but this is a pretty old processor. But here you could see, for example, where is it? Okay, so here's the floating point data path, right? So this is where floating point operations are done in the CPU. And here's another thing that's interesting is just to multiply a floating point number is a huge portion of the die. And this is just the data path, which I'll talk about the data path in a little bit. And then over here, we have the integer data path, which we will talk about. It's pretty big as well. So this right here, so as you can see, this is like a zoomed out version, but if you were to zoom in, it would be like, thousands of, or actually, I think I could use the number that's like usually thrown around, like you could probably fit, billions of transistors on this thing with the current technology. So it would be a lot. You could make a pretty big circuit with the current transistors, which is what, allows us to get faster and faster. So anyways, let me go back. Okay. So yeah, so the thing to take away is we have transistors. Transistors become digital circuits, which are, these logic operations, which, AND, ORs, NANDs, NORs, XORs, XNORs. So yeah, boils down to just these, basic logic operations. So that's like the makeup of a digital circuit. It just uses logic gates, ands and ors and nots and things like that. So CPUs are just a specific example of digital circuits. A CPU is a digital circuit. A GPU is a digital circuit. Any kind of like most circuits are digital circuits. Analog circuits are kind of being phased out right now because of the fact that you don't need a big analog circuit anymore to handle complex things. You could just have an Arduino or some kind of microprocessor, and then have it hooked up and handle all these digital signals, these ones or zeros. So I just want to talk about this a little bit. So Moore's law is dead. Some people like to say it's not, but it is. So Moore's law isn't necessarily like a physical law, it's an economic law, or not law, but more like observation, which was that every year the number of transistors on a chip doubled, but the price of a per transistor went down. So that's what, everyone was so happy about Moore's law, because every year they could expect more transistors, which then led to faster computers and cheaper computers, which means more money. But now, as of late, as of 2000, really, that kind of ended. And there's another thing called Dennard scaling, which also helped out. But now, like that was it. So basically, like a single core processor can no longer just, be made faster and faster because of issues of heat and also because of issues of cost. So that's when hardware designers decided to explore multi-core processing, parallelism, having multiple threads. Although threads have been around for much longer than multiple cores, been around since the 70s actually. But they're being more used now because single core performance has kind of reached a plateau. So now, like, a lot of architects are looking into domain specific computing. So, remember that CPUs and GPUs are special cases of digital circuits. Like a CPU is, something that handles general computing, right? Like logic, arithmetic, floating point, arithmetic, as well as logic, as in like deciding, if this, go to this condition, or if this condition, go here, if that condition, go there, etc. Right? And GPUs mainly focus on graphic processing. But now, since Moore's law is dead, people have been talking about more domain-specific computing. So if you'll look at I guess I could pull it up. Let me. How do I? Oops. If you look at the new, for example, Apple chip, where is the die picture? Right here. So, for example, they realize, everyone's in Apple realized this, which is why they are, they're trying to get ahead of everybody, my opinion, making their own chips. Yeah, it is. It is like a city. So they realize, can't put Intel chips on our phones, can't put Intel chips on our tablets. We want domain-specific hardware, which is why they've started to, and a lot of companies are starting to do this. They're trying to basically hire a lot of hardware designers to design specific chips. So that's why you'll see things like here's the neural core, 16 neural core engine for basically like machine learning and AI. So that these kinds of operations aren't loaded onto the CPU, which can be very inefficient. The CPU can now load AI operations or machine learning operations like matrix multiplying and things like that to the neural engine, which can then, spit it out to the CPU. So like this is an example of a more modern chip that uses, instead of like having, something insane like a Threadripper, right? 32 cores, which will take up like the entire die space. If you look at the Threadripper, it's huge, right? It's like enterprise server level CPU, right? It's huge. You could use some of that die space for other things. And Apple decided this design choice, which was instead of having RAM off the chip, they have RAM on the chip. So here you have 8 16-bit channels, or not channels, but the RAM is on the chip, basically. So they have 8 gigabyte or 16 gigabyte RAM on the chip. Normally it's off the chip, right? Like if you build your own computer, if you open up a computer or laptop, you'll normally see like the RAM modules on the motherboard, but not on the CPU. But for Apple's case, they decided instead of having RAM separate off chip, they decided to design it into the chip. So that's something. So that's what I mean is that now hardware designers are, instead of going the traditional way of just having a faster and faster, bigger core CPU, they're now looking into more specific designs, more exotic designs, you could say.
So what if you want to upgrade your RAM? Do you have to replace this
Yeah.
or what? Oh,
Yeah.
And would that be more costly? Or
For the user.
oh yeah. And I wanted to ask you that thing with the core neural engine. Is that something new? I don't know what that is. The
Mhm.
16 core, the one that on right in the middle on the bottom of
Mhm.
that picture. What it is that just something new?
Yeah, it is new. Normally you see these things on GPUs. They have uh, they'll have like, especially like NVIDIA, right? NVIDIA is known to have
Mm-hmm.
ML AI cores in their GPU to basically um, offload you know machine learning operations, which usually involve a lot of matrix multiplication, vector matrix multiplication, addition, just a lot of linear algebra basically. Um, but that can be very expensive for a more traditional CPU, um, in terms of like performance. So instead of having, telling a CPU which is designed to be like a jack of all trades, you can offload that data and those instructions to the neural engine, which then are more specifically designed to handle matrix multiplications and vector matrix addition, multiplication, what have you, which is what a lot of AI ML stuff is. It's just linear algebra, calculus. Um, so you have this hardware that's designed specifically to do that, basically, and then you could just send it back to the CPU. Or I'm sorry, I keep pointing this as the CPU. This is not the CPU; it's the GPU. Um, but yeah, uh, I think this is it. 4 Firestorm performance cores. And here's another thing that they're doing that's interesting is that um, they'll have a lot of like ARM and the Apple M1. They'll normally split or at least have like a ratio of high performance, high power CPUs with lower performing cores, low power cores. So basically, like when your phone's idle or what have you, or you don't really need all that extra horsepower, it'll switch to only using, for example, I don't think it's here, but I'm just saying, for example, here you would have, so these are 4 Firestorm performance cores. Oh no, here they are, right here. So here you have the ice. These are marketing terms, right? Ice storm, firestorm. So we have 4 efficiency cores, which are the more like high power, performance cores, and then over here you have, or I'm sorry, over here you have the performance cores. Over here you have the efficiency cores, which are low power, maybe not as fast, but this is more efficient because you use less power, right? When your phone's idle or you're not using, you know, applications that require a lot of, horsepower. So this is what I mean. This is a very domain, like for example, the Apple M1 is a very domain specific CPU, right? For phones. Um, they obviously put the RAM on the chip because they want to make the phones thinner and smaller. And then they want, to split, instead of having one 8-core CPU that just uniformly uses power and every core is just firing at, full speed. That's going to drain your battery. So that's why they have this split. And then that's why they also have this neural engine to do AI ML stuff, which I'm guessing is like for Siri and any other application that requires machine learning or AI. And then also have this huge GPU. Well, it's not that huge. I mean, NVIDIA card has like thousands of CUDA cores, right? That do graphics processing. But yeah. So this is an example of a domain specific. So like designs are getting more and more exotic, more and more specific, instead of, let's just buy Intel's chip, or let's just wait for Intel or AMD or ARM to make a chip that we can use on our products. Apple's one of the, I guess, loudest when it comes to, we're going to make our own chip, designed specifically for what we need. And that's what the M1 is. And that's why you see them putting it in everything, in the new iMacs and the phones, putting it on all the phones, and now on the tab, the Pro, what's it called? The MacBook. No, not the Mac. I forget. The something Pro. One of the tablets. They're using the M1 chip as well. Because yeah, it's a good design. It's kind of ubiquitous, right? It could be used almost anywhere. It's very power efficient, and it's got a lot of horsepower. It's pretty fast. So yeah, so that's kind of an example of domain specific CPUs instead of relying on the more traditional. Let's just wait for Intel to come up with the next chip design, right? Okay, so okay, I need to move a little faster. So another thing to consider that's super important in computing is memory, right? And if you look at this diagram here, you could see analogies, right? So registers are the closest form of memory to CPU, right? Like a register is, normally for example, a RISC-V CPU has 32 integer registers where you could store data to do, multiplication, addition, XORing, ANDing, what have you. That's the closest. So the analogy is thoughts in your head, right? Information in your head. If you wanted to remember where you put your keys, you just think, right? And your keys appear in your head and you know where they are. Now on-chip cache, right, is a little bit further, but it's not that far, right? If you had to, with CPUs normally have to go to memory, have to store things in memory, right? Because the memory on the CPU is really small, at most 32-bit times 32. So that's, can't do my math right now. But that's how much, bits or bytes of memory you have on CPU. If you wanted something a little bit bigger, like an L1 cache, which is closer to the CPU, that's like you getting a book in your room, right? You just get up off your desk, go to your bookshelf, and you pick up the book. It's pretty close, right? Onboard cache, which is usually off chip, or not off chip, I'm sorry. It is on chip, like L2, L3 cache would be if you're back in school and you had to walk to campus, which is 10 minutes away, right? And then main memory, which is probably even further, would be, for example, if you were to walk, or not walk, but drive, this an hour and a half is driving. If you were to drive from Berkeley to Sacramento, it would be an hour and a half. So it's even further when you go off chip to onboard memory, right? If you were to go on your desktop from the CPU to main memory, would be the equivalent of driving from from Berkeley to Sacramento, any hour and a half trip, right? And then if you were to go to disk, it's the equivalent of going to Pluto from Earth, about 2 years. And I'm not sure what speed that is, but I'm pretty sure you can calculate that. And I'm not sure what a tape robot is. I don't remember what this was, but the point is, the further out you go, the longer it takes. So that's why cache is super important when it comes to CPU, because, in order to process large data sets, you need the space to transmit and receive data. So that's why cache is extremely important. And then going back to the M1 chip, here you can see the cache right here, the SLC cache, which is shared. If you look, it's shared between all the cores. So this is probably an L3, L2 cache, which then goes out to all the different RAM modules, which is on board. So having it on chip helps making it a little bit faster when it comes to memory, even though memory nowadays is really fast. So, okay. Are you guys with me? Am I boring you guys? You guys have any?
This is great.
No, this is interesting. I really like that picture showing the analogy of things. So it gives me really a better idea of what we're talking about. But yeah, this is very interesting.
Cool.
Jason, so
Just make sure. All right, just making sure. Yeah. So, all right. So I'm gonna go pretty because I already spent like a while on that. So this is a example of a CPU. This is the RISC-V CPU. So typically a CPU has the RISC CPU. Can't say the same for a CISC, which is complex instruction set architecture, and RISC is reduced instruction set architecture. So typically you have this structure. Here you have DMEM or data memory, and then over here you have the ALU or arithmetic logic unit. This is where logic operations like XORs and ANDs and additions and subtractions are done. This is all integer stuff. Because integers in binary are way easier than floating point, as you saw on the die. Like just to have the amount of logic it takes to do floating point multiplication is huge, especially if you want to optimize it, right? You can have something simple but not very fast. And in today's world, that's not good, especially for graphics. Graphics usually focus a lot on floating point operations. And then over here you have the reg file, or this is where the registers are for these high-speed memory. And then you have instruction memory, which is where each instruction is stored. Normally like an assembly instruction like add x1 with x1 and x0 or something like that, or sub. This whole thing is what's turned into a binary string, which is then stored in the instruction memory. And the reason why it's separated is to avoid what's called a structural hazard, because the last thing you want, and this is going to be like a huge stall in your CPU, is if you're trying to, for example, let's say you're trying to write something to memory, right? And it takes like an hour and a half, right? Your hour and a half. So while you go off to go write something, if you want the next instruction, you got to wait, because this unit is being used to write to memory, and that just basically, it would make a CPU like incredibly slow. So that's why they separate it. You have two. Here you have for instructions, and here you have for memory. And then PC is the I can't remember. It's a counter to basically like which instruction are you at. And normally it's +4 or 4 bytes or 32 bits. So we're assuming a 32-bit processor. So if you wanted to go to the next instruction, you would add 4 bytes or add 4 in hex. So this is the structure of a RISC-V CPU. So you have load store instructions, which basically move things to memory, either bring things from memory or send things to memory, main memory. Register instructions, register instructions. So basically operations that are involving memory that's on the CPU. Register immediate instructions, and immediate's just another word for constant, like what we all know as constants in math, right? Like instead of having to store, if you wanted to add 5 + 3, right? Instead of having to store this, in a register and this number in a register, you could just have one number in a register and then provide a constant, or this is 3, in order to add 5 + 3. And then we have our branch instructions. So these are like if statements, like switch cases, we all know in C. Basically, you check for a condition, and if it's true, something to think about is if you're linearly going down a program, right? Instruction. So, you have 0, and 4, and 8, and, so on and so forth. You're gathering all these instructions. Let's say, you hit a condition, right? If this, then that, then you need to jump to another location in memory to retrieve those instructions, right? Either forward or backwards in memory. So that's what branch instructions do. They check for conditions, and then they branch out to either, you go up in memory or you go down in memory to fetch those instructions. And then jumps are like unconditional branches. So no matter what, no conditions, you're just going to go here. You're going to go to this next, this location in memory to retrieve those instructions, which then flow through the pipeline or the data path. This is what's called the data path, basically, where you start from, where you grab the PC counter, basically tells the memory, it's keeping track of like what address it's at, and then it tells the instruction memory unit to fetch that instruction, and then it flows through this data path, which then commits or accomplish or finishes a single instruction. That's the data path. So the RISC-V ISA, or the instruction set architecture, is the contractual agreement between hardware and software. So like, so when you write a compiler, for example, you're guaranteed, if you're using a RISC CPU, and this was the problem before C, was that anytime IBM or Intel or any other company came out with a new architecture, they would have a new instruction set architecture. So it was like a huge pain to rewrite an entire standard or a language that can work with the hardware. So the ISA is basically like the guarantee, right? It's like the handbook that says, okay, these are the instructions. You don't need to worry about what's happening in the hardware. No matter what, if you use these instructions, this is what you're going to get. And this is what's used by people who write compilers to basically translate whatever higher level language into that specific ISA. NVIDIA does something different, which is that they're constantly changing the ISA, but they use they have their own language, which is called CUDA, which is used by developers, and that doesn't change. So despite the fact that that they use different kinds of, they have new instructions that they add or they change the architecture, no matter what, CUDA doesn't change. Underneath that layer, they might, improve it or change it a little bit, but, no matter what, So that's a way to keep that kind of software consistency, which is also a huge problem in hardware if you wanted to change something. So these are the instruction types: R type, I type, S type. R type is usually like register to register, register to immediate. B types are like branch instructions. J types are jump instructions. These are load and store instructions. And then these are like big immediate instructions. Here you could see, of the 32 bits, you have the opcode, the destination register, and these are just encodings to figure out what operation you're trying to use. The two register operands here, RS1, RS2, and this is another encoding to figure out like what operation are you doing? Are you doing an XOR, an AND, blah, blah, blah. And then these are just immediates. So you can have, for example, in the I type instruction, if you wanted to add, which is called like add I, store it here, and then you're adding this number, x3, let's just say this is 3, and 5, this is your immediate. If you want to add these, then the size of the immediate is basically 12 bits here. So you could have 12 bits in your immediate. So this is the architecture. This is or not the architecture, the ISA, the instruction set architecture. So these instructions work in the, why can I go back? In the pipeline, in the data path here. So let me clear this. Right, this is the complete RISC32 ISA. Here you can see, this is the opcode and everything you need to know. Basically, this is all in the handbook. 37 instructions are enough to run any C program, basically. So, and there's other more complex instructions, which I'll definitely not talk about. More like system instructions. So this is the complete data path. Just like the things I mentioned, you have your DRAM here, the ALU, which is the arithmetic logic unit, the branch comparator, which determines branches, the reg file, which contains the onboard memory, an immediate generator for the immediate instructions where our operands are not in memory. We just want to generate like a number. Here we have instruction memory, and then we have our PC counter, which determines which instruction we're fetching from memory. And then down here, this is probably like one of the most important parts, is the control logic. So this is what signals to the different units, like what we're going to use for every instruction. Yeah. So, all right. You guys have any questions about the data path? Or...
Nope.
No. Okay. Cool. So yeah. So this is basically a CPU. You get a binary string that contains this data, which then signals to the architecture what you need to do. Basically, that's a CPU. Ultimately. So this is, I'm gonna breeze through this, but this is what cache is. If you're not familiar with caches, like I said, it allows us to fetch memory much faster. Well, the fetching itself isn't, the speed is the same, but if we're reusing the same data, for example, if we're accessing an array, which is contiguous portions of memory, then instead of having to go fetch every single element in the array, we could fetch like a big chunk of the array. And that's already in the cache, which then we can use, the CPU can use a lot quicker. So yeah, we don't want to, die waiting for memory to come to us. So these are like cache misses. This is a little bit more into caches. So in a cache, like I said, you have to fetch from main memory in order to put it into the cache. So you have these what's called misses, or if the CPU asks for memory and it asks the cache, do you have this? These are the kinds of no's you're going to get from the cache. You have compulsory misses, which are what happens when the cache is empty and you need to go fetch it. So it'll miss, and then the cache will go retrieve that memory. So by the time you come back, it's there. You have capacity misses, which are basically you try to fetch something from memory, but the cache is full, so it has to evict a line from the cache, which means it has to go to memory and fetch that. And by the time you come back, that line should be there. And then you have conflict misses, which happen when basically like you accidentally evict a line you're going to use. So the way like the math works out when calculating, and this is all done on the memory address of whatever data you're trying to retrieve. If they conflict, for example, if you probably see this a lot in a linked list, where a linked list is not a contiguous set of memory, right? It's just like random locations in memory. So every time, let's say you try to go back, but you just retrieve something that had a similar address, then you just evicted that for the new memory. So now you have a conflict miss because those two addresses now conflict, even though you're trying to access both of them. So these are the kind of misses. There's another kind of miss, which I will not talk about, but it has to do with cache coherency, making sure if you're using a multi-core system, you got to make sure that if, for example, if you're running threads, that the memory is coherent, right? What one core sees is the same as what another core sees. So things get a little bit more hairy when you start introducing multi-core. These are the kinds of associativity. I won't talk about this, but if you're curious, you could, check it out. But these are the different types of caches you could have: direct map, two-way set, four-way set, fully associative. It's just different ways of calculating the address. Here you can see You have these 3 sections for direct map: a tag, an index, and an offset. And then if you notice, as you go down towards the associative caches, the tag bit gets bigger and the offset bits get smaller. Or the offset usually stays the same, but the tag and the index is what changes. So typically, most modern caches have like a balance between being direct mapped and being fully associative. So you'll see like 2-way or 4-way associative caches. And like I said, this is a way, and they've all figured this out through like statistics, and just seeing like just documenting people using computers. Well, not people, but them using computers, and just figuring out by running like test algorithms like vector multiply or matrix multiply, or using a lot of recursion and things like that, running all these like benchmark algorithms, they figured out, it's best to just kind of balance it. So yeah, this is just a way of calculating the address to avoid things like conflict misses and capacity misses and things like that. You want to reduce the number of misses because those increase the time it takes for the CPU to get memory. Okay, so even though we have cache and we have our CPU architecture, and the RISC-V architecture is like as simple as they get. Like normally this is what's used like in classrooms and stuff that's like initially taught to people, to students, to learn about how architecture works. But like this is a very simple design, right? Because when you introduce an instruction in memory here, you have a clock, right? Which, for example, you could say like this is 100 megahertz, which is, 1 over 100 or 1 million seconds, right? So that's how long one clock cycle takes at 100 megahertz. So this is one cycle. So like in this architecture, a single instruction will take one cycle. But you have this thing in digital design which is called the critical path. So if you were to, for example, when you see like this little triangle here and it says clock, this is called a register, or this is memory. So from here to, for example, here, where these are in sync with the clock, these are synchronous circuits. These are not synchronous. These are asynchronous. They just, whatever they get, they just spit it out whenever. So when the CPU gets an instruction, it has to travel this entire data path over here. And in order to meet timing constraints, you calculate how long it takes. Like, for example, like going back to when we talked about transistors, it takes a certain amount of time for that voltage to go high, right? And the last thing you want is corrupt data, right? You want consistency. So in order to meet those timing constraints, you got to meet the hardware halfway there, right? Like you got to be able to time these things, or time these things so that the hardware can accurately read those signals. So from this register all the way to this register, let's just say like the fastest it could go is 100 megahertz, right? So this bottlenecks like how fast we can, pump out an instruction. So it'll take, that many seconds to complete one cycle, which is one instruction. And there's other optimizations that people do. There's this thing called pipelining, where you add extra registers here, here. You add them between the units so that you shorten the data path, which then means that you can run it at like gigahertz, because now for data to flow from, for example, here to here, it's a lot faster. And then with pipelining, in each phase of the pipe, right here, you have like instruction fetch, instruction decode, execute, memory, and write back. So you would have what's called a 5-stage pipeline. And then at each stage, you have a different instruction. But that's okay. Even it won't take one cycle to complete instruction, but that's okay. It will take many cycles. but the amount of time it takes to finish a cycle is now faster. So instead of running at 100 megahertz, now you go by the longest or the critical path, and you can increase the clock speed now because the critical path is much smaller. So you can run the clock a lot faster. So that's like that's like one of the optimization techniques, right? And having a cache, and now you can have like a pretty fast system, right? But that's not fast enough. Not in today's age, right? This is definitely not fast enough. So besides cache, pipelining, yeah, so I'm just going to mention two optimization techniques. One's called out of order execution. So instead of executing instructions one at a time as you get them, like let's say, one instruction doesn't use the integer unit, the ALU, but another instruction uses memory, right? And it takes a while to get memory. So, but that instruction to do memory is ahead of the integer instruction. But in order to be in order, you finish the integer instruction first, and then you do the memory instruction. With out of order, you have a scheduler that sees, and this is what I wanted to show you guys, is that this unit here, this control logic, this handles the out of order complexity. So like there's a lot of logic that goes into doing out of order executions to handle, the scheduling for instructions and making sure that even though it's completing at out of order, the commit or like what the program sees as instructions finishing is in order. There's a lot of logic. Oh, sorry, go ahead.
So I'm sorry. I just have to jump in because I recall the conversation that I had with some people, coworkers. So how do we do this? If you have the time constraint, the optimization, is this something we have to do down the, how do we, okay, so I have encounter, we have time constraint, we have race conditions, and I'm looking at the optimization concept, out of order branch prediction. Where do we do this, Jason? Is this something? How do we accomplish that? I mean, let me explain this because I recall very clearly that we have certain situation where, like I said, we need to have time constraint, race conditions, and I'm looking at some optimization thing like out of order branch, things like that on the hardware. But how do we do this on the software part? I just don't. I'm having a mismatch thing here.
Mm-hmm. Well, software, like race conditions have to do with threads, right? And that is like a software issue. Mm-hmm. Like that's when you have to use like locks and make sure that if the threads are sharing memory, mm-hmm. If you're like, for example, if you're incrementing a counter, you want to make sure that the threads don't increment the counter at the same time and you like mm-hmm. double count and things like that.
Right.
That's like software, right? But like these out of order things, it's all abstracted away. So as a software designer, you don't care. You don't worry about that.
So as a hardware designer, what is that what you're talking about now?
Mm-hmm. And this is crucial because mm-hmm. this is what allows like CPUs to be really, really fast. And this is this is what's called like speculative execution. So like the CPU will speculate, mm-hmm. okay, I see these instructions, right? And mm-hmm. you have like, you could see ahead and it depends on the hardware, like how far ahead you could see. And then the scheduler will like basically determine, okay, well, I could do this first and then, these other ones before I do the ones that are ahead of it or before it, and finish those instructions first because I can get more done by scheduling the later instructions earlier and basically like mixing it around and doing things out of order.
I see. So this is everything we're looking at is done in the hardware, right? So, okay. That's pretty good.
Yeah.
I didn't think about all this stuff. I mean, obviously I don't know anything about hardware, but I'm just thinking all this, the concepts involved in the hardware, right? Yeah. Oh, go on. I'm sorry. I'm just thinking in my head now. So
Yeah, that's why the logic takes up like a huge portion of the die just to do out of order execution. But it is probably like one of the best optimizations
Mm-hmm.
to exist since like the 1950s. Like this is
Mm-hmm.
out of order execution is a result
Mm-hmm.
of like decades
Mm-hmm.
of improving architecture, and it's what's used in all modern CPUs is out of order execution. Um, excuse me. Um, so the other thing is branch predictors. So these kind of go together, and branch predictors. So like out of order execution just means we right. So here we have a complex pipeline, right? So before we had the instruction fetch, which went to the decode, and then now you have this new thing called an issue, and the issue is basically like the scheduler. So this thing basically has it's like a buffer that stores instructions and will determine which instructions to do first. For example, here we have like out of order completion, but in order issue. Or this just means like we receive the instructions in order, but we finish them out of order. Um, so like a floating point divide, we assume has a latency of like 4 cycles, right? Multiply has a latency of 3 cycles. A load, like load from memory, is 1 cycle, and the divide 4 cycles. Subtract and add are like 1 cycle, right? So if you were to do it in order, right, you do the first instruction here, and it takes about 4 cycles. So that means you got to like hop between these units, go to the add, and then you write back, and then you're done. So that's like 4 cycles, right? Going from the instruction fetch, the decode, the issue, the add, the write back, and then you're done. You commit the instruction. If you were to do it in order, first you issue the divide, and then you issue the load, right? But then you have this gap here, right, where you have to wait until 1 finishes before 2 can finish. And then you issue 3, and you have to wait, you issue 4, and then you have these gaps, and then 3 finishes, so on and so forth, right? So this is in order, right? You basically have these little gaps where the CPU is doing nothing. You have unused resources here. So out of order exploits that and says, well, why don't we use the extra space to do other instructions, which may be ahead or before. And that's what the out of order does. So here you can see we issue 1, we issue 2, 2 finishes first, then we issue 3, then 1 finishes, we issue 4, 3 finishes, we issue 5, 5 finishes, we issue 4 and 6 and so forth. So now we're using all the resources. So now we don't have these like wasted cycles, basically. We're using everything we can get. And software doesn't care. Like this is all the software sees is in order complete, basically in order completion.
Yeah.
So that's out of order execution. And then branch predictors, basically like if you were to get, for example, if you had a branch instruction, right, which is like, if x1 is equal to 0, go to this location for the instructions. If not, then keep going, linearly down PC+4, PC+4, going to the next instructions, right? So like if you had a branch condition which said, if this is true, go down here. If it's not true, keep going linearly down, right? So, but the thing is though, is that the branch has to go down the pipeline, and you won't know if the branch condition is true until the write back stage. So you would have to wait, however many cycles for the branch to finish in order to know if that condition was true. So typically there's like branch policies, which is like always assume true or always assume false. And let's say you always assume true, right? So you assume it's true. So at the instruction fetch, instead of the PC counter counting +4 relative to its current location, it'll now retrieve this memory location and start counting from 4 from there. and let's say it's wrong, right? You assumed it's true, so you start fetching this, you fetch this, and you have all these instructions down the pipeline. Well, if it's wrong, you have to kill every one of those instructions. You have to flush the pipeline, and that can lead to wasted time. So that's why that was like another huge like drain on CPUs is that. So that's also part of, and then like this is even more important for out of order execution, because if you do instructions out of order and then you're wrong about which branch to take, that could be a lot of computation just to revert back to your previous location, because you completed the instructions out of order, and let's say you modified memory, then you're, that's a lot to manage. So branch predictors are like extremely important for out of order, and they're extremely important anyways, so that you have some kind of system, right? And I won't talk about it. There's like really a lot of exotic kinds of branch predictor architectures out there. But that way, like you increase the probability that you're right. So there's a chance you're wrong, but that chance gets smaller and smaller. That's the branch predictor. So typically branch predictors, like the most simple kind, they just kind of learn from behavior, right? So like if, like let's say you're in a loop, right? And you're constantly like going back, doing the same thing, then you train the branch predictor, oh, so the next one's going to be true. The next one's, like, let's say it assumes the first one's false, right? It has like a state, the first one's false, and it gets that one wrong. Okay, so you have a branch penalty, right? You lose some time. But then it says, okay, well, let's just learn from that and now assume it's true. And let's say you're constantly looping, well, that branch prediction is always going to hit true. So now you're like, instead of being one, let's just say like it loops 10 times, right? Instead of being like wrong half the time, you're now wrong like only, 1/5 of the time. So like,
Jason, I have a question. Sorry for interruption.
no
So
worries.
you mentioned about branch policy. So the branch predictor overrides that. Is that what you're saying?
Yeah.
Because it learns by, okay, got it.
Yeah, so it learned, that's the policy. Like the branch predictor determines the policy. Like how are we going to treat this branch instruction? Are we going to assume it's true, or are we going to assume it's false? And that's going to be based on like a system of a way of determining if it's true or not. That makes sense. So yeah. So that's the branch predictor, which is also a part of this. So the branch predictor and the out of order execution take up a lot of die space. But as you can see, sorry, I'm just as you can see, like it's a big part of the optimization. Like it's what allows CPUs to be really, really fast and correct most of the time with high probability. And usually they have high probability, like 90%, in the high 90s. These branch predictors are usually very correct. So with that in mind, here are the branch predictor slides. So I won't talk about the details, but yeah, it's basically what I said. And just so I guess like just some statistics, improving from 90% to 95% prediction accuracy removes 50% of branch mispredicts. So if 1/6 of instructions are branches, then move from 60 instructions between mispredicts to 120 instructions between mispredicts. So we could throw away this many instructions on a mispredict, so on and so forth. And even more with a superscalar just means instead of issuing one instruction at a time, we issue like 2 or more at a time. And we do instructions in parallel. So modern CPUs, you can think of them as superscalar, out of order, branch predicting architectures that are just aggressively optimized to give super fast CPUs. So yeah, those are branch predictors. So now, okay, so boom, this is what I worked with. So this is the Berkeley out of order machine. It's a free open source architecture, which you could find online. If you just look up boom or Berkeley out of order machine. So this is the architecture, which is not too different from what we've seen. You know, we have 4 fetch units, and this is the out of order logic here. This is all the out of order logic. And then we have 3 pipelines. We have an ROC accelerator. This is just some accelerator. These are the write back stages, so on and so forth. And this is the branch predictor here. So as you can see, out of order and branch predicting is like a huge portion of CPUs. So here's another diagram of it. Has an L2 cache, L1 cache, and it's just a bunch of details you don't really need to know. Just we have branch prediction, we have out of order execution. So now Meltdown and Spectre. So Meltdown basically exploits the virtual operating system space. So both of them are related, but Meltdown is a lot easier to mitigate than Spectre. Meltdown you can mitigate by separating the virtual address space between the operating system and the user. If you separate those two, then Meltdown won't work. But normally they're together because it's a lot faster to have the user and the operating system on the same virtual memory space. And virtual memory is just a way of making our memory, our RAM, seem a lot bigger, and it's also a way of abstracting and making the operating system have multiple programs running at the same time and not collide by allocating virtual memory and make it seem like, you know, each program has its own memory space. So Meltdown and Spectre, the way they work is they exploit those optimizations, the branch prediction and the out of order execution. So basically, and the cache, those 3 things. So caches, you know, we know that the way caches work is they exploit two things, spatial locality and temporal locality. So like if we're constantly accessing the same space, right, or the same spaces, the cache will now have those spaces in the cache. So, you know, when we try to go out into memory, you know, instead we go out to the cache to retrieve those things. And it turns out that caches are not, you don't have a separate cache per program, right? Like every program doesn't have a cache. Everybody shares the same cache. No matter what the core is. Like I said, there's cache coherency, so all the cores see the same cache. So what Spectre and Meltdown do is that they, I guess to put it simply, they train the branch predictor. Or let me show the code. Where is it? I think if I explain the code, it'll make much more sense. Oh God, it's ugly. So here we have like the branch prediction training. So we assume that, or actually, let me go back. So for this example, we're on a boom machine, right? We assume a small kernel which acts like an operating system, right? That shares a virtual address space with the user, right? The upper gigabits of memory are for the operating system, excuse me, and the lower, or the upper portion is the operating system, and the lower portion is the user space, right? And normally, if any program tries to access the operating system memory space, you get a segfault, right? It says you can't access that memory because it checks permissions. The hardware checks permissions, and it says no, kill that instruction. This instruction is invalid. That's what the operating system handles. But in order to make things fast, these are done in parallel. So the out of order execution executes, for example, a load from memory. So it's executing, right? It's going down the pipeline. It already fetched the memory. And for all you know, it's already in the cache. But then in parallel, by the time it figures out, oh, wait a minute, this instruction's invalid. This user, is not supposed to access that memory. It'll kill that instruction. But even though it killed that instruction, it already fetched from memory and it was put into the cache. So now that memory, which we weren't supposed to access, is now it's in the cache. So going back to the code. So Spectre relies on what's called, they call it the Google researchers call a gadget, the Spectre gadget. And our Spectre gadget is basically a vulnerable piece of system code, a syscall. So here we have, where is it? Leak. Leak is right here. So leak is basically allowing us to, for example, I don't know why I can't see it here. I think I'm blind. Here it is. Here's the gadget. So we have memory somewhere, right? And in this case, it's, or for my lab, it was pi. We have the number pi in hex, right? And we want to access it. It's in the unprivileged or privileged memory space. Only the operating system can access it, right? As users, we can't access that space. So here we have the syscall, which takes an index. Don't worry about the shift. And like, for example, accesses an array and it returns the array, right? But a certain portion of that array is not for us to see, right? If we go outside of that, we return -1, right? We return an error. But if it's valid, then we take the data and we return the data, right? All fine. Seems like it's okay, right? And this is okay. This is safe, technically, right? On a software level, like this is safe, right? Because if we go out of bounds, we don't allow out of bounds checking, right? So, so on a software level, this is okay, right? But on a hardware level, what we do is we train the branch predictor. So we call this syscall multiple times correctly. So now the branch predictor goes, oh, when I see this instruction address, I'll execute it. This is correct. So the branch predictor will always assume true. So what Spectre does is you train the branch predictor a certain number of times. And this is also a part of the Spectre optimization to make this faster, is figure out like what is the minimum times you need to call this syscall in order to correctly train the branch predictor. And that varies depending on the branch predictor hardware you're looking at. So in my case, it was like 64 times. And then what you do is this thing, it's called prime and probe. Is there's two ways to leak the data. It's prime and probe and flush and load. I want to talk about flush and load, but we do what's called prime and load. And you can see this is all out there. If you just look up, I think the Google white paper is out there, and they actually have a really cool demo, which I'll show later. So after we train the branch predictor to always assume true when we call this syscall, we have what's called priming. So what we do is we calculate, we assume I think this is a like 4 kilobyte cache, L1 cache. Typically L1 caches are pretty small. So we based off of that, right? And this is also assuming that we know the address that we want to leak, right? We know the gadget, and we assume that this is not super important, but we leak 1 bit at a time. So we know the size of the cache, the L1 cache. We know the address. So based off of that information, we could figure out which, if we go back here to this diagram, right, we could figure out based on the tag and the offset and the index, we figure out which line goes where, right? But I'm sorry, but for this initial, for the priming, we want to make sure that that we're fetching cache lines, right? Like these books, right? These are individual cache lines in the correct spots, right? And for that, you need to do like some calculation and figure out like exactly what address relative to the current array you need to access, right? That's, you know, fairly trivial, right? You could easily figure that out. And so what you do is you basically train the cache, or you prime the cache. So you fill it with just, you know, BS, right? So now you know that you filled up the entire cache, all the spots that you want. So if there were a cache eviction, you would know because you just primed the cache. So then we execute the leak. We now this is where we insert the malicious array index, right? And we try to access something we're not supposed to access. But the hardware is going to do it. The hardware, so we cleaned out the cache, right? We primed it. We trained the branch predictor. So now when we call the syscall with that index, it's now gonna evict a line that we've already primed. We know what's in there, right? It's just BS. We don't care what's in there. We primed it, and now that a line from there is going to be evicted, and it's now going to contain the leaked data, which is basically like, I think it's a byte, right? So now we probe, and the way we probe is we basically check the number of cycles it takes to access the data. So we re-access the array, right? So we re-access locations that we know in the array, which are already in the cache, right? Like, because we access, like if we have an array, you know, with like, say 5 numbers, right? 1, 2, 3, 4, 5, right? And we fill the cache, right, with this, right? 1, 2, 3. And this is like super simplified. This is not like, there's definitely a lot more details that go in here, but I'm just like, for the sake of understanding on a higher level what's going on, I'm not like using exact numbers and things like that. So like we filled it, right? This is our array. This is the cache. We primed it already, right? It's filled with this array. So now when we call it, we evict, for example, this line. And then let's say, I don't know, we have pi. Like I said, this isn't exact, so just like bear with me. So now when we probe it, we're now checking, we're accessing. We're like, okay, what's this? What's this? What's this? And then boom, bingo. We now, instead of having like when we access these, we should have like low cycle different cycles, right? Because it's in the cache. But if we access something that now hits a high cycle count, then we know that at that address is the leaked data, because when we when we called that instruction, it evicted that line for the leaked data. So now, and then we check to see if, and then there's like, you got to check with thresholds, and if the cycle count crosses a certain threshold, then you know you have a byte of the leaked data, and you just output that. Yeah. So that's essentially how Spectre works. So you train the branch predictor, you prime the cache, you execute the illegal instruction, right? You get a seg fault or whatever, the operating system says you can't access that, but that memory is already in the cache. And then you probe the cache by accessing the same array. And when you hit that high cycle count, you know that this line has to be evicted in order, this, 3 pi has to be evicted in order to get the 3 back into the cache. So that's how you know you have the leaked data. And that's basically how Spectre works in a nutshell. Meltdown does a similar thing, but it relies more on virtual address space, whereas Spectre doesn't. It works on anything, basically. And that's what makes modern CPUs so vulnerable, is that, these are optimizations that all CPUs have. They all share the cache. They all have branch predictors. They all execute out of order. So anyone can do this. And there's obviously a lot more. And you can look at the white page, the paper that was written by the Google team. They have an appendix where they actually have code. There's demos, videos. I was going to show one. I was going to show you a demo. Sorry. A demo that I did. Let's see. Can you guys see this okay?
Now we can, or now I can.
Okay.
Yeah, so
I'm going to speed this up.
okay.
Because this takes a while. Mine was pretty slow. It takes a while. So let me just fast forward a little bit. Yeah, so it's basically running, and this takes times, right? Because you have to prime the cache, and for this cache, it was assumed that it had, and if a cache have eviction policies, the eviction policy for this cache was random. So you had to figure out, like, statistically, how many times do you have to prime the cache in order to get the correct cache lines, because it would randomly evict lines. So here you can see I'm leaking 1 byte at a time from the restricted memory space, and it takes a while. There's 24. That's the next byte in the pie, so on and so forth. Yeah, 3F. There it is up there. 3F. So there you can see. That's basically how Spectre works, and I think. There's also this. This is the Google demo. I didn't think it was that informative just watching it. They're just kind of showing that their app works. But you can go online in the demo, and you can actually play with these parameters and run the demo yourself. And then you can visually see how the caches are being primed and probed in order to leak the data. So yeah, that's about it. So
Jason, I do have a question. I'm just not clear in my head. When you were showing that other stuff, you talked about the high cycle being, that's when you know the, I don't know how the wording you said, but I don't understand what you mean, the low cycle, the high cycle, where you draw the array and, the cache. I mean, how did you know that you drew the picture, so it's not on your presentation. So can you just explain that the high cycle versus the low cycle, where you know the I don't even know what the word you were used, but you know what I'm talking about, right? It was you were showing the Spectre what page were you on? I can't remember, but you were showing your code, I think, the white page, the whatever that white page that you had your C code on there. So so can you just explain? You don't have to go to that page, just kind of explain what you mean when you look at the low cycle, then you were saying the high cycle indicating where that's a place that you can, I forgot, you can actually grab, did you say what did you use the word?
They'll leak the data.
Yeah, leak the data. So you drew a picture that has 3 as the high cycle versus 1, and 3 was the place that where you can leak the data.
Oh, right.
So,
yeah. So because we know that like we know that main memory is further away from the CPU, right?
Mhm.
So so like that's why when we prime the cache, right, we fill it with the values in the array, right?
Mhm.
I'll just use like letters A, B, C, D, blah blah blah. We fill the
Right.
cache, we prime it with data that we intentionally put there that we're
Mhm.
going to access again.
Mhm.
So initially, like let's say the cache doesn't have this data, right? It's like, for example, let's just say the cache is completely empty.
Mhm.
Then when we try to access the array, right, A, B, C, D, blah, 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 we have to go to main memory. The cache has to go to main memory. And that, if you were to count the number of cycles, it would be high. But if we were to access the array again after the first time we access the array,
Mhm.
then the data in the array would be in the cache.
Mhm.
So we do it, we access the array enough times so that
Mhm.
we know for sure that the cache is filled with the data in the array.
You okay?
Yeah.
You know, I see what you're saying. Okay.
So when we
Uh-huh.
access the leaked data like pi,
Uh-huh.
right?
Yeah.
Then the cache is already full
Mhm.
of the stuff that we access. So it's going to have to randomly evict, and this just happens to be there's different kinds of eviction policies, but we just for this case it was random, right? We randomly pick, a 1/4 probability that we pick, I don't know, A. We evicted A. So now A contains pi because we got to make room for it in the cache because that's just how
Mhm.
cache works.
Mhm.
And so now when we go back and probe the array and re-access this array,
Mhm.
then we count. We're like, oh, this is high, but this is low, this is low, this is low, because this is already in the cache, but A is not in the cache anymore, it's pi. So we know that when we access that memory location, we have that. And now that data has been leaked.
Oh,
Yeah.
okay.
And that's how we can leak the data because it's already in the cache, which means when the CPU fetches that data,
Mm.
we're fetching the leaked data.
Okay, thanks. This is very, very interesting, Jason.
Yeah, that's pretty cool.
Oh, it was just like, wow. Thank you so much. This is the first time I really, start getting understanding of this, but this is, wow.
Do we know if there was
Uh,
ever any actual? I know there were POCs of this, but I don't believe this was ever actually exploited in the wild.
Yeah, I don't think so either.
That's just what I recall. That it was more of a finding, and then the world caught on fire because of it. But I don't believe it was like a 0 day that was ever exploited. I could be wrong, but I think from memory it was more of a, hey, we found this, so everyone needs to fix it ASAP.
yeah, I know.
Otherwise,
I remember. Everybody has to fix it. Well, not me, but I know the people at work, they were busy.
And then I remember there was talk of the performance
Uh-huh.
hit that was going to happen once it was
Oh, yeah,
patched
yeah.
because
Right.
of
I
that. But I
heard
think
about
one's
that.
patchable and one's not, or something. I forget, or they were both, but it definitely affects
Spectre's
the
Meltdown's patchable, but Spectre is not. You have to
right,
turn off out of order execution in order to patch. So
right.
you basically
And
have.
well, I was saying both of those are, like you were saying before, they were attempts at making things more efficient.
Oh,
So
yeah.
then you patch it and then you lose that
That was the
performance.
reason why.
Exactly.
No, you can't make it as efficient, right? That's why the performance got hit. I get it. You can't. Uh,
Yeah.
so, hmm.
Otherwise, you have to completely redesign the hardware, which is, I
Mm-hmm.
mean, if you're Intel, what are you going to do? Like, you already shipped out,
Uh, mm-hmm.
thousands and millions of these CPUs that
Mm-hmm.
are
Mm-hmm.
vulnerable.
Yeah.
Basically all modern CPUs use this. That's why ARM and AMD and Intel,
Mm-hmm.
they're all vulnerable to this because
Mm-hmm.
it exploits these optimizations. Obviously.
Mm.
But yeah, I don't think anyone's used this. I don't never heard of anyone using this in the wild, but I think in the example that Google did, they did it on JavaScript. So even a JavaScript could use this exploit. They did it. So it was in their demo. So they're saying that web-based applications could basically use Spectre.
Mm.
So I don't really know. It's really, really hard. This is really like you really,
Right.
really have to understand
Yeah.
how hardware works and what
Uh-huh.
you're working with.
Oh yeah, definitely. You have to know both, right? This is your homework. Is this your, I'm sorry, is this your homework project? You might have told me about it. I can't remember now.
Yeah, it was a lab. This
A
was
lab, right? Yeah. Okay.
yeah. So, but they greatly simplified it so that we can actually do it. Because like the paper itself is like super long and the code's like super complex, and it's just it's really difficult. And I'd imagine like your typical criminal hacker just
Mm-hmm.
they're looking for a quick, I'm assuming, I mean, most of them are just looking for a quick buck and are just like using tools that they probably bought some, black market or something. And, it's not easy to do. It takes a lot of understanding and skill to successfully.
Right, but I noticed for state sponsor thing, they can go really,
Oh yeah,
yeah,
for
it's not
sure.
script kiddie stuff. They really, the advanced persistent threat, they go really, they have the whole like business that, that they hire engineers just to do this kind of stuff. So yeah, I mean for other things, the phishing, other stuff, probably, I don't know. I don't know enough. I'm just saying very highly sponsored, state sponsored. Yeah, they do have really complicated. They have the engineers just show up like people, like you and I show up at work and do their stuff. All they do is try to hack, right? But they really study really hard and they try to get it to work. But this is so cool. I mean, thank you so much, Jason. I mean, this is like, I have to admit, this is the first time I actually understand what's going on. I mean, I heard about all the system admin was trying to busy doing this, but I never had a chance. I don't need to study this kind of stuff for my work, right? This is really cool. They're taking advantage of optimization, the hardware, in order to get into this. Well, this is not like Dante said, it's not really, nobody really supposedly got, this is not like a 0 day, you know, day thing, but the idea of the concept of this is just amazing. People look at all those different things, right? Like
Yeah.
you have to know both hardware and software in order to do this. But
Yeah, it's really creative. It's really, I mean,
yeah, it's
like,
really interesting. How do
you,
people come up with those ideas?
it's just
I mean,
thinking about these things really, really hard for a long time, I guess. Like,
yeah.
I mean, even the designers themselves had no idea. I mean, they were just trying to optimize hardware. They never thought
Mm-hmm,
that.
mm-hmm. Yeah, they're just trying to optimize, right? Yeah. So anything you do that could cause, hmm, you have to be really careful. Anything you do could be a place where people can turn into a playground, right? And just hack you. So, but thank you so much. This is really great. Um,
For
oh,
sure.
some people, I'm just looking at chat. I haven't looked at chat. Some people left, but they wanted to congratulate you on your internship. Oh, that was Dennis. And congratulations, Joe said, good luck with your final year in undergraduate school. So they're all at the chat now, the Zoom chat. So
Sure.
great. So
Appreciate it.
so is this from last semester or this is from this
This
semester?
semester. Yeah, I took a
Uh-huh.
computer architecture course this semester, and
Ah,
yeah.
great. Hey, we really hope that you will make sure you can present. I'm glad you reach out and said, hey, you can present on this topic. This is really fascinating. We're always learning, I encourage anybody here from maybe Cal State Long. I encourage everybody to continue. Learning is just something we always do, right? Can just keep learning, and this is really cool. Thank you again, Jason. So, what are you going to present next? I'm sorry.
I don't know.
Something you doing at Cisco Systems? No, that would be proprietary. Sorry
Yeah,
about that.
yeah, I can't
I
really.
know that wouldn't be something you don't present anything about work anyway. So I think we'll be looking forward to have you present at your fall semester, right? That you
Mhm.
will be your last semester of your undergraduates. So great.
Sure. Yeah.
So Dante, what do we do right now? There's only 6 of us right
Yeah,
now.
no, I
What is
think
that?
we call it